Okay, welcome to this Polonius walkthrough. So the recording has started. So let's see. I'm going to share this document, I guess. Let me just move this to a fresh window so we don't have a bunch of junk. Share. Okay, hopefully you all can see that. And I'll try, let's see. I'm going to see if I can do it through like GitHub links more than, jumping into an Emacs buffer. We'll see how it goes. So looking at the agenda, how data is collected and packaged up in rustc. So before that, let me go to Polonius. Oopsie. And probably, yeah, whatever. So here's Polonius, and if we look at this, we will find, there's, sorry, let me jump back a bit. There's Polonius and Polonius engine. Polonius is like the testing harness. It's not actually used by rustc. Polonius engine is, and within it, there's this facts file. And this is kind of the interface to rustc, right? And so it's totally generic over what exactly represents a region, a lone, or a point in the control flow graph. These are always some new typed integer, basically, but the actual new types are not in this crate, so it's generic. It might be declared in rustc and so on. And you have here this basically one vector for each of the inputs to the analysis. So the one that we are going to look at most closely today, I guess, or the one that we're looking to, let's say, replace, is this region live at. And the reason is that most of these, like the control flow graph edge, for example, is something you can directly get out of the mirror control flow graph. You just kind of walk through the control flow graph structure, and anytime a node is connected to another node, you put a thing in the vector. There's really no interpretation there. It's just a different representation of the data structure. And to a certain extent, that's true for all of these. A little bit less so for something like killed, which I don't think we've even talked about, but that basically says there's an assignment at this location, like x equals foo, and there's a borrow of some subpath of x, like x dot bar, and therefore you put it in the vector. But it's still fairly easy to understand. Like, there's not a lot of interpretation involved. Liveness is different. In liveness, what's happening is the compiler, we're going to see, is going to do a liveness computation of figuring out what's live at each point, and then encode the results of that computation, which is itself a fixed point computation, into this vector. And that's kind of silly. It would be better to do, we'd like to move these, like, I guess that's the real distinction. Anything that requires iteration, ideally, we would move into this, into Datafrog or into Polonius. Okay, so that's our goal. So where does this all facts get populated, or where does the kind of compiler communicate with Polonius? That's a good question. Let's see if I can find it. So not here, apparently. Hold on a second. Actually, I should pull up a few links. Uh-oh. I have to turn on my VPN or something. Sorry, one second. How does this even work? There we go. Okay, sorry, you can't see what I'm doing right now, but I'm trying to connect real fast so that I can at least do some greps through the source code and answer some of these questions better. There we go. So let me just do that real fast. Okay. And nope, wrong directory. That'll do. Okay. Yeah. So Okay, so one place we might look at in the borrow checker, there's this module called facts. And you can see here that it grabs from Polonius engine the all facts structure, which it renames to Polonius all facts. And then we export a sort of version of this that uses the compiler's new types, right? So where Polonius talks about a region, in the compiler that's represented by this data structure called region vid, where vid stands for variable ID. And borrow index is what we call a lone. Location index is a point in the control flow graph. So you can see that they're just integers, but they have their own little local names. So this is like local instantiation. And then this trait, this is like an extension trait to add some methods to it. So you can ask if it's enabled. And the write to dir, all that does is really dump these into files that are in the format that Polonius can import. And the point of that is that rustc can run with an option to dump these files so that you can then run Polonius in a standalone way without the rest of rustc and just reproduce the actual analysis. So that's where the facts are, like, that's one part of it at least. Let's see, the next part is going to be oh, yes, I was in the right place. Oh, I'm just searching. I don't know what's going on. Let's try this. I think I'm hitting the wrong keys. Okay, right. So this function, compute regions, this is a big part of the borrow checker, the non-lexical lifetimes borrow checker. And one of the things it does is to, if Polonius is enabled, is it creates the facts for Polonius. Right, so here it will say, if I'm enabled, which means that you pass the correct flag to the command line, then I create an instance of the all facts, which is empty, and store it in this variable. And then we run, and you can see we give this variable, for example, to the type checker. And the type checker will emit facts like that one lifetime has to outlive another, or sorry, one region, whichever. So it generates some subset of facts. And then here we're adding some more facts into that variable, saying, okay, let's extend that with a set of universal regions or free regions, and so forth. And again, here, this constraint generation. So where all these things are basically populating the facts table, right? And the generate invalidates, this is saying, invalidates is how Polonius says, well, this action would be incompatible with that loan. And at this point, we're done, and you can kind of see that by the fact that we're going to write out, if they've asked us to write these things to files, the user, then we will do so. And the other thing we'll do, here's where we write to the files if we are asked to. The other thing we'll do is if we're asked to use Polonius in order to create our errors, then we actually invoke Polonius here, right? And this output comes from the somewhere here. Comes from the Polonius engine. So this is actually the sort of main way that Polonius executes. And you can see we pick the algorithm. We get it from a string, but we tell Polonius to figure out the algorithm and compute the result. And that goes into this variable, Polonius output. So it will have the either none, or it'll have the results that Polonius gives back. And we put them in a ref counted thing so that we don't have to, so we can clone it because they're immutable once they get created. And then Polonius output happens with that. That gets returned. And it's not really that important for the point, so I'm not going to go into it. But that Polonius output, what it contains, I guess I'll go into it at this level. If we jump back to the Polonius engine now, oops, wrong place. The Polonius output is this data structure. And the only thing in here that these maps are all going to be empty. These are only used, as it says, for debugging. But it will contain a list of errors at each point. Basically, at this point, there was an error because this loan. And so the actual, later on, the error reporting code is gonna, if we're in the sum case, it's going to walk through those errors and use it to report errors. Okay, so that's kind of a quick walkthrough of, let's see, of how data is collected and packaged up and how it gets fed to Polonius. I guess the thing I didn't cover is the liveness in much detail. And part of that's because I don't exactly remember, but let's take a look where that actually gets computed. I think it's probably in constraint generation. So the way that liveness works today, let's see, is this true? Somewhere, I don't recall where, we have a liveness computation that I'd have to find. Let's see, region, live, no, I guess it's not here. Let me take a look. Okay. Oh, I see. Yeah. So in the borrow check, in the type check, there's a directory called liveness. And in this liveness code, we actually, this is the current liveness computation. And it's a little bit complicated. It's a little bit more than just liveness in the traditional compiler sense. So normally that would just be like, is this variable used later? And we do that, but we distinguish a few different kinds of uses. In particular, drops, the implicit drop that occurs when a variable goes out of scope is a little bit different from an actual use where you wrote it manually, because sometimes we can tell that drop won't access some of the data, and so we don't have to consider it to be used by the drop, which can be, lets us be more flexible. But we do this computation and we append it in. And so what our initial goal, I think, would be not to change anything here, but just to add to it that we're going to add a new set of facts, which is probably two things. Or it's certainly where is each variable defined and where is it used, right? And I mentioned that there's two kinds of uses. So let's see, let's scroll down a little bit. How does this code work anyway? I remember writing it, but not. Well, I don't know. We'll come back to it. But compute live, it must be this computation here. Oh no, that does a different thing. Well, somewhere in here we do this computation and we would do this. We would find the set of uses from each point, and basically we'll wind up with an addition to the vector. We're going to wind up with adding to all facts something like variable. First of all, we're actually going to have to add a new parameter for variables. Let's call it V. So where we now have the regions, loans, and points. There'll be something like, let's call it variables. And then there'll be a variable definitions probably it's like a vector of V and P. So a variable definition occurs at some point, and there'll be like variable regular use is, which is also a vector of V and P, and would just mean variable is regular used at some point, and things like that. And we could have a variable drop uses too. Mean that the variable is drop used at some point, and drop used means that it's that implicit drop I mentioned. Probably just start with this one. Once we get the basics set up, it'll be easy to add the rest.
So that would of course be the raw data.
Why is okay. So okay, good. Let's jump. So now we kind of covered these 2 points, and I guess we covered a little more like what we would want to add to that for liveness. So what about this mapping? So if we were going to do liveness computation, there's going to be some rules that are going to say something like the variable is live. Let's say we have these variable regular uses, variable job uses, and so on. And you might say anytime that a variable is regular used at a given point, then the variable is regular live. So that means like on entry to that point, the value in that variable is going to get used. Right? And then you might have something like, if there's an edge from P to Q and the variable is live at Q, then the variable, and probably we want, and it's not defined at P, then it's going to be live at P also, right? So we'll walk backwards to the control flow graph. So that's like our basic rule. And now what I want to show you now, because you've seen a lot of rules like this, is how do you map these sorts of rules into Datafrog? It's not entirely obvious. So we won't map that actual rule because we don't have that rule yet, but we'll map a different rule. And if we go to the naive computation, let's find, the subset is pretty similar. So if you recall, there were rules in the naive computation, make this a little bigger, like this one. Well, let's start with a simpler one. This is a transitive rule. This says, if at some point P, R1 is a subset of R2 and R2 is a subset of R3, then R1 is a subset of R3. Pretty simple. And the way that that gets encoded, I'm going to take this over to my how Datafrog works. So this is the rule we wanted to put in. This is like the data log rule. So what's going to happen in Datafrog's model is that this variable subset, or this relation, I should say, subset, is mapped into a program variable, like a Rust variable, which you see defined right here. So oh, I see we have this iteration. So first of all, there's going to be, the first thing in Datafrog you always have is some kind of iteration. And what that basically means is this is a computation. And an iteration can have associated with it the various variables which represent the relations you're computing. And so when you write iteration.variable, you give it some types. Region, these correspond to region, point. So it's a tuple. Basically, this tuple is what the variable consists of, a set of those tuples. And then the reason that thing is called iteration is because there's actually a bit of Rust code here. We're doing a fixed point iteration, which means we're continue working, adding things until we get no more changes. So the way that happens in Rust, like Datafrog itself is just some libraries that you can invoke, and the actual iteration is here. So we keep going while it's changed, and then we do this call. And this corresponds to this rule, right? And what this from join does is it says add in to the current value of subset, add any new tuples that you get by joining, in the database sense, these two other variables. We'll come to those variables in a second. So joining meaning take the set of tuples from one and the set from the other and see where they have overlap. So in this case, these are expected to always be two tuples where there's like a key and a value 1 and a key and a value 2. That's the type. These types have to be mapped to that. And so these keys, wherever the keys match up, you get a callback. So what you have here is, this is the key, and this is the first value, and this is the second value. So what is this R2P and R1P going on? Well, these are also variables. They're like temporary variables, basically. They're not the real, they don't even appear in the data log, but they're like intermediate variables that you would use. And the way they're defined, they're exactly the same as subset, except reorganized. They're like a database index, if that means anything. Just reorganized to identify what the key is, right? So this from map says add into subset R1P all the tuples that are in subset, but apply this closure first. So we're taking the subset tuple, which is the three things all equal, and we're reorganizing them so that we have the key we want, which is basically we look here, we see, oh, this thing, what these have in common is that they're at a specific point, and R2 appears in both of them, right? So we want to join where the second part of this tuple is equal to the first part of this tuple, and the third parts of the tuple are equal. So first we extract out the first part, and we make a map that has the first part and the point, the first region and the point. And then we have another one, R2P, which is basically the same, except it's going to pull out the second part. And then we join those together. And now, so what we essentially have here is the R2P and the R1P. And now you can start to see where the naming convention comes from. This underscore, like R2P, is telling you, okay, this is the key. This is the same as subset, but with this key. And this is the same as subset, but with that key. And so when we get the callback here, that where these names come from, that kind of comes from this data log code. The R1 is the second half of this tuple, which in our data log code is R1, and the R3 is the second half of this tuple, which would be that R3. And then this is the final result, R1, R3, RP. So you can kind of make this in a fairly mechanical, it's like hard, it's not trivial, but it's mechanical to convert the data log rules into this Datafrog rules. That's the basic structure. There is some more fancy stuff you can do. In particular, there's from leap join, which is more efficient and kind of nifty, but also kind of wacky. Let's see if we can walk through how it works. Let's see if I can remember how it works. So what this rule is trying to do, this is somewhat similar to the rule that liveness will ultimately want. What this rule is trying to, oh, come on, that's the one thing I hate about, not the one thing, but it is one thing that I hate about Dropbox paper. So when you paste in something like that. Anyway, so, right. So what is this saying? It's saying if you have that R1 is less than R2 at P, and there's an edge from P to Q, so it's going forward, but there's an edge from P to Q, and the region is live at Q, then we have R1 is less than R2 at Q. So we've got to kind of join together in some sense the, we want to take all the existing subset tuples and take out the point where they are, join that with the control flow graph edge to get another point, Q, and we're going to join that with these region live at computations to see if the R1 and the R2 all match up, right? And there's something interesting about this rule, which is that, first of all, the only variable in the sense of thing that changes as we iterate, so that's what a variable is in Datafrog. I didn't actually say that explicitly. There's actually two concepts, variables and relations. And relations are essentially your inputs from the point of view of any computation. So they're not changing during the iteration, they're fixed. And the variables are the things that are actually growing at each round, right? And here we have this, all of these are relations. These are all base inputs that don't grow, with the exception of subset, and that's also the output. So there's like a recursive thing going on. And in that case, we have a particular optimized method called from leap join that can be more efficient in the way that it's implemented that you can use. And what it does, so how it works is, actually it doesn't matter that they're the same, I don't think. It just matters that there's one variable and then some number of relations that it gets combined with. And so it has the same basic structure. You call from leap join, and that adds things into subset. And then you give that one variable here. That's the first parameter. And then the rest of the parameters are a definition, are derived from the relations, so the things that aren't changing, the inputs, and they tell you how it should be like combined with the value of that variable. So in this case, the first one, extend with, what that says is, first, look at this tuple here, R1, R2P, you see that in each case it's R1, R2P. We're going to pull out just the P value. And this config edge relation, yeah, this is just config edge like so. So we're going to take that, whatever gets returned from here, we're going to match. This has to be a 2 tuple. We're going to match to the first part, and then we're going to take the we're going to match to the first part, and we'll take that Q value and we will use it later on to make new tuples with, right? So that's what happens here. So basically here we're basically doing this join, and then actually I'm a little surprised by this, but that's okay. And then what this is saying is, well, that's what the code says, so it must be right. So this is saying, right, kind of, oh, I see, right, because these Qs all have to be the same. So kind of the same thing, same kind of join, except that in order to, all of these extend with calls are going to produce a new Q value, basically. They're all proposing new, what is a possible value for Q? Because all the rest of the variables came from the input. So that's the only thing we're extracting. And the way that they're doing it is by doing this joining, right? And so the here we're saying, okay, pull out the R1, match it on this thing, which is already a 2 tuple, so that's okay. And that'll propose a Q, and this will propose a Q. And then for all the things that they all proposed in common, you'll get a callback where here was the input value that we passed to each printer, and here was the Q they all agreed on, and now you can return a new value, something roughly like that. And there's some other methods and options. So extend with is the basic one that lets you say, pull out some part of the variable, use it to match against the relation, and pull out some new thing that you can use to make new values. Then there's also like extend anti, which lets you say, if you pull out some parts of the variable and if you find any match, then remove this, like then you can kill it because it's not supposed to fit. So that would be useful for something like not variable defined, right? And there's some other things, filter with and filter anti, which is kind of the same thing, except here you're always joining the first half, and the second half you're either proposing or killing, right? So if you say extend anti, then it would say anytime that you have a match and it has a Q, that Q is not part of the output. And filter with and filter anti take these entire tuples here, or these tuples, or I forget exactly, but they don't propose new. They don't have that key value thing. It's more like you're just checking, is this tuple part of the set or not? Anyway, we can get to that, but so that's it. I have to go, but we just made it with a covery of how sort of Datafrog and Polonius work. We won't get to this, but that's okay. It's not very important. And we kind of did this, what it would mean. So I think, right, that's just part of this section. Any brief questions right now in 0 minutes? Okay, good. Also, you're muted. At least I didn't hear you. But, then I will see you on Zulip. Thanks, everybody. And I'll post this up shortly.